Obviously, we're under quarantine, but does anybody have some quarantine spring break plans lined up for next week? Might go to the living room. That's the spirit. TV shows you want to catch up on? Video games you want to play? Parks, New York City parks you want to visit? Ooh, gardening. What kind of garden do you have, Hareem? Is it a community garden, or do you have like a yard? Or that's dope. I just joined the community garden down the street from me, and I'm hoping we get some good weather Saturday, so I can go get some plants in the ground. Anything you're excited to grow, Hareem? This is turning into a gardening class. Yeah, stay away from the community. Should be some more people going. Shizota was just, ooh, pumpkins. That's dope.
So we should wait like what, 5 more minutes?
Let's wait another 5 minutes or so. Some regulars that aren't here yet.
Mm-hmm.
I've never grown pumpkins before. It seems like it would be fun. Grown other squash, but not pumpkins. I haven't totally planned it out yet. I'll probably start some tomatoes inside soon. I want to grow some herbs. I want to grow probably some greens, some lettuce, and some kale and stuff. But I think it'll be mostly tomatoes. If I had a backyard, I would be going hard on like a strawberry patch or some blackberries or something like that. But don't know if it's worth it for the... I guess I could see if the garden wants to start a patch. I don't know if I would be around when they start actually bearing fruit, though. Welcome, Shizota. What kind of dog do you have, Carlos?
I have a pogo.
A what?
It's a pogo. It's a mix between a pug and a beagle.
Okay, yeah, I think you told me that before. Pugs are super cute. Yeah, that sounds awesome. We might be getting a cat for quarantine, a little animal to keep us company.
We'll say having a pet is fun, man. Like I told you.
Might have a smaller crew tonight with all the midterms and projects due and everything, but we'll give it another couple minutes. How have your guys' online classes been going in general? Have things kind of settled into place, or are people still figuring out how to make it work and stuff?
It was quiet.
Gotta finish my drink now so I don't spill it all over my computer again. Yeah, cutting down on the commute's big deal. What school do you go to, Mel? Nice. I went to City too. Where do you live? Yeah, I did the Brooklyn to City commute. For me, it was a little over an hour. The old three train, three transfer commute. Um, all right. Are you gonna queue up the Kahoot, Carlos?
Yeah, sure.
We can get started here in a second. Welcome to San. People are still trickling in. We can give it another minute. Mike, welcome, welcome. What TV shows have people been watching while they're stuck inside? I've never actually watched The Office, so I'm watching The Office for the first time. It's been kind of funny
Man, it is a classic, man.
to see all the memes and everything that I already know in their original context. Um, No, I was just deciding, Meldon. I was about to answer your question, and then I was like, wait, I want to hear what TV shows people are watching. For your TV shows in the chat. So Meldon asked any resources you guys would recommend to help us get better at these topics. So yeah, it's my goal at least to do a better job of dropping a couple things into the channel every week. Related to what we talked about in class to just kind of reinforce some things. So I put some videos in the channel that you guys could check out that are related to last week's topic and this week's topic. As far as general resources, um, I guess it kind of depends on exactly what you're looking for. I will do Coursera classes comes sometimes and have kind of mixed success. I like MIT OpenCourseWare a lot for sort of like linear algebra and some of that sort of stuff, but I don't know what they have regarding like machine learning and things like that. And yeah, that's what I was just going to say. Carlos mentioned Linda. Do you have any resources that you like, Carlos? You're on mute. You're on mute, Carlos.
Thank you. So yeah, man, I know of this website where they have an introductory course for data science. Okay, here I have it. Yeah, it's from Harvard. So I'm going to share the link with the group. Here's a repo.
Oh, nice. This looks dope. But usually, what I end up doing is just if I need to, look up a specific piece. Usually, there's like a towards data science is a good medium, um, whatever medium calls those things, hubs or whatever. Um, so I'll usually find an article about like a specific topic there, or Geeks for Geeks. I like their articles a lot. But yeah, this GitHub looks like a good place for sort of like a overview of
Hmm.
general content and stuff. I say let's get started. I think we've got most people that are going to come in. So welcome everyone. Good to see you guys again. So today we're gonna continue kind of what we started last week. We did an intro to machine learning and we focused on classification. So today we're going to focus on regression and hopefully kind of reinforce some of those topics we talked about last class. And we're also the notebook set up this week to give you guys more of a chance to kind of program along and things like that. Before we get into that, Carlos is going to do a Kahoot to start us off. That's part of the class.
All right. Welcome, everyone. Got this. Okay. Can you guys see it? Okay. Can you guys see it? One more. And that's it, right? No. We need three more. That's it? I think we're missing one person, right? One or all right, let's start now then. Good. All right, so next question. Okay. Do you guys have any questions about this? Actually, let's make it at the end because you're gonna have similar questions to this one. Hey,
Ooh, leaderboard change.
okay.
You guys are good test takers. Process of elimination.
Good.
So anyone gonna catch Sar? Did Sar win last time too?
All right. All right, guys. Okay. Welcome, everyone.
Any
Can I,
questions about the Kahoot or anything from last week before we dive into this week's material?
questions? Can you guys see the notebook?
Yep.
Yep. All right. So let's we can start now then. So welcome everyone. Today the lecture is going to be about regression, and what we're going to do is basically we want to cover a data set, which is the wine data set, and what I want you to do. Well, actually, let me explain a little on. So the topics for today, first, we want to cover the brief theory of linear and multivariable regression. Then I can say it's the roadmap to creating a model um, in data science. Like first, we'll start by defining the problem. Then we do some feature engineering, which is part of the exploratory data analysis. Split the data, uh, scale the features. We train the model, and then we will tune the parameters of the model to optimize to minimize the error and optimize the output of the model. And at the end, we want to assess the quality of the model by see how the model performs in with data it hasn't seen before. So yeah, these are the libraries we want to use. We can start by loading the libraries. After we load it, I guess most of you know about. I mean you have to know straight linear regression. As Steve said that last week, the classic y equals ml equals x equals m times x plus b. So basically, the coefficients and the exploratory variables are multiplied and then sum up together to predict the outcome, which is y. Well, in this case, we only have one parameter, which is x. I mean, one feature, and this is the bias, which is the initial value, and this is the coefficient of the only feature we have. But in real life, we can have many features. Let's say instead of having one, we can have many features. And this is the idea. Like every coefficient gets multiplied by the corresponding feature, and everything is add up to see what the outcome of the problem is. That's a straight progression. And how can we evaluate the model? We can evaluate the model in, you can say, in some metrics. The main metric that to evaluate the regression model is the mean square error. And what the mean square error is the estimate of the actual value, which is this part here, and the estimate, which is this. Basically, it's this formula here. Inside this, you get the error, and then you square the error and take the mean of the sum of the errors. And this here is called the cost function. This, we're not going to talk much about it, but I think it's something that you should be familiar with, especially when talking about machine learning. What the cost function does is that it is responsible for updating the coefficients of each feature during training, so that way you can minimize the error of the output. All right, so data science principles to build a machine learning model. The first thing we do is we define the model. In this case here, we're going to be working with the wine data set. And this is what we are going to do. For the wine data set, there are two data sets in the repo. Like you can check. We have the, yeah, wine quality white CSV, and wine quality red CSV. So what we are going to do today, I'm going to work on this data set, and I want you to do the same thing, but using this data set here. So we can start by importing our data frame in pandas. Read CSV. We want to check if everything is right. So as you may see, there is error we have when we load it. That means that we have to set the delimiter to the semicolon. Delimiter. Limiter. we loaded now. Everything looks right. Um, who's who hasn't loaded the data set yet? I guess everyone is following along. So after we load it, check the shape. I'm pretty sure yours has a different shape. You can check the info, see if there are any no missing values. So apparently there are not missing values in this data set. Do you guys have any missing values in the white wine data set? If you don't, please send a message. So that way I know that you at least you loaded the data set and got the info. Okay. Sir, any missing values in the white wine data set? Thank you. Okay. So you can also check for any no's if you have no's. And the way to check for no's or DF is no. And then we can sum everything up, make sure. And then we check the descriptive statistics of the data. Like what is the maximum value, the minimum. Right. Yeah. So we have each CCD, it has a minimum value of 4.6 and a maximum of 15.9. So basically, most values are positive. I want you to take a look at this part here, like the free sulfur dioxide, this column, where the minimum value is 1 and the maximum is 72. So compared to the other ones, it has actually no, total sulfur has the largest magnitude. We have density, pH, sulfates, alcohol, quality, and yeah. So basically, we're going to create a model that is going to help us to make wine. I guess making wine at home during this quarantine, it would be a nice activity for the spring break. So yeah, basically we check some of the columns and we see like some of the columns have similar names. Like you see a CCD here. So there are two types of acid, basically. And you also have the sulfur. It has like there are three types of sulfur, like free sulfur dioxide, total sulfur dioxide, and sulfates. So I just want you to have that in mind for later on. And yeah, we can proceed and see, like, maybe we can create a heat map and see how it looks. So you guys remember, like you can create a heat map doing the per plot. Something I forgot to mention is that one of the features of the data set is the quality of the wine. And right, so this is the matrix plot. So regarding the quality, we'll have a question for later for that. But yeah, this is the matrix plot, and we want to see like if there's any difference of the features of what we need to make the wine and the quality of the wine. And we can get the information by doing hue, and then Right, it's hue and select quality. So what hue does is that it assigns a different color based on the class. So just to make sure. Please go. Okay, quality. I know it takes some time. Okay, yeah. So this is what you get. You get the matrix plot, and you can see is because you have like 10 features. Basically, it doesn't fit in the whole stream, but you can see here it's very small. And this, well, it tells you which color belongs to which class. So it's something you can have in mind for later on when you start working on a project. So we can define the correlation matrix. Can we do that? Or yeah, make sure. And then we can create a heat map of using the correlation. I want everyone to do this part here, the correlation, so that way you don't get behind. After you get the correlation matrix, I got this code for you, so you don't have to. So what this code does, it creates a correlation matrix and then returns a heat map of the correlation matrix. Yeah, it takes a minute. It does finish running. Yeah. I know. Oh, I haven't defined this function here. So I guess everyone is who's getting behind. Is everyone following me? So anyone who's getting behind, please let me know now. Okay, so I guess we can continue. So yeah, we can take a look to the correlation matrix. And as you can see here, like if we look at the, I'm sorry, before I proceed, because this is something we didn't discuss last week, just in case if you have any questions, here's the formula for the correlation. Should have covered this before going to the heat map. So this is the 2 points correlation. And what this means here is the mean value of feature X, and this is the mean value of feature Y. So now let's go back to the heat map. So yeah, remember that at the beginning I said that there were some features that had similar names like the citric acid, as well as volatile acidity and fixed acidity. I mean, if you look here to the heat map, like fixed acidity and citric acid, it has a high correlation. So this means that it could be wise to drop one of the two later on and see how if it improves something in the training of the model. And basically the same thing happens with the citric acidity and volatile acidity. And this happens because so basically citric acid is the acid that stays in the wine, and volatile acid is you can say the one that flies, so it doesn't, it becomes like a gas. So that's why it has a negative correlation. Plus two, it has a high correlation. So again, this is something that we might consider to drop later on. And basically, we have a similar case with the citric acid in the pH. But I don't want to discuss pH. This is not a chemistry class. This is a machine learning class. Okay. So what do you do when you want to make a model on a data set? Then like you check the features and then you get to a point that you have to split the data. So the way to split the data is basically if the data is not it's not a sequence data, meaning it's not like a 10 series data. I would say this is the proper way to split the data. So basically what you do is that first you divide the data into two parts, which is the training and the test set. And then you divide the training set into two parts, which is the training set and the validation set. And what you do is that you use the training set to train the model and the validation set to see how the model performs and seeing data. And then you tune the parameters of the model. Like you change a few things up to a point that the minimum error of does not change. And then that's when you basically done training the model, and then you use the test set to test the model. That's the last thing you do. Like the test data that you split at the beginning, you don't touch it. You just leave it sitting around into you actually need it to test the model. So the way to split the data into training and testing, we can say, okay, call this X, which is actually not Y. Uh, so our Y is going to be alcohol. And our X is going to be everything else but not alcohol. So we drop this column for the X. Just to make sure. Take the sheet. So yeah, so the X has 11 columns and the Y has only one. And you see the whole data frame has 12 columns. So let's see what the quality of the wine is and how it is distributed and more based on our data. So we can do a histogram. And we see that the minimum value we have for the quality is 3 and the maximum is 8. And actually, I would say the minimum value should be 1 and the maximum should be 10. But that might happen because the two is two data sets, one for white wine and the other one for red wine. So my guess is that white wine has the may have different values. Please, someone tell me what is the minimum value and the maximum value in the histogram of the white wine data set. No one. Come on, guys. Yeah. Which part? Jorge. Oh, splitting the data. Okay, this part here. I mean, this is the X and the Y. We haven't actually split the data yet. Okay. What is U? What does U error says? MBN. Oh, never mind. So it's good now. Okay, I see. All right, guys. So let's continue. So can someone please tell me about the histogram of the quality of the white wine? What is the minimum? What is the minimum value of the smallest of this bar here and the maximum of this bar here? Come on, guys. Are you guys following me? All right. So tell me, sir, where you at? Okay. So my question is, you got to this part here, to the histogram, like making the histogram of the quality. Yes. Okay. So my question is, you see, I have one, two, three, four, five, and six bars. How many bars you have? Okay. What is the value of this bar? Okay. So Jorge got seven. Okay. So are you using the white wine data set or the red wine data set? Jorge, which value do you got here? Okay. I mean, I can check later on, but yeah, let's continue. Is I guess who's getting behind here? So I guess everyone is up to this point. Okay. So I guess we can continue. So remember last week we used the train test split. So I guess you're gonna have to fix this part if you have a different name for X and a different name for Y. Okay, so I'm doing this part here, which is called stratify. And the reason I'm doing stratify is because since I have a class here and some of the classes are unbalanced. So what a stratify does is that it divides the same amount of classes, the same proportion of class 3, class 4, class 5, 6, 7, and 8 to the training and also to the testing part. So you see, I do it here and here as well. So here is where I do the first split. The first split is the training set and the testing set. So run this. Here is the second split. This is where I take the training set and divide it into training and validation. And then we can check. So in this part here, I said drop the quality from all ads. Can someone tell me why I don't want the quality in my as part of my features in to train the model? Can someone have a guess? All right, so let's think. So the data set, what I have in the data set is this. Basically, it's the recipe to make wine. And based on the recipe, we want to determine how much alcohol we want in the wine. So is quality an ingredient? No. We're trying to guess the alcohol because we're doing regression. If we're doing classification, then we will try to get to guess what is the quality. So my question is, yeah. So now we're trying to determine what is the amount of alcohol of the wine, because we're doing regression. So now my question is quality an ingredient to make wine? Nobody? Exactly. So then that means we have to drop the quality because we only want the ingredients, right? Drop quality. So for basically we're gonna have to do it 4 times. Okay. So we drop this, and then we can check on this one.
Carlos, could you explain how you've named the variables really quick?
Oh, sure, sure. So yeah, yeah, I always use some weird names to name variables. Yeah, that's my style. So here I have the edge. Yes, Mike. So here is the training and the edge for training. This is the edge for testing. This is the Y for training and the Y for testing. This is on the first split, and for the second split, yeah. So basically, the TR is for training and TS is for testing. And what I have here is RDB is basically the V stands for validation. That's how I know is the second split, and for the first split I don't have the V. So yeah, like oh, I think we dropped it already, so we can check if it was dropped in the first 5 rows. And as you can see now, we don't have the quality anymore. So we only have the acidity, volatile acidity, citric acid, residual sugar, chlorides, free sulfur dioxide, total sulfur dioxide, density, pH, and sulfates. So the other part that we want to do is we want to bring all the features to the same scale. And one technique to bring the features to the same scale, like remember when I told you before, all right, so when we do describe, like for example,
Mike's got a good question, real quick, about why we split into validations.
okay, so let's say last time where we split into training testing and why they were split up. But how is splitting for validation different? All right, so this is the thing. You need to make two splits, one for training and testing, because you're going to use the testing data at the end when you finish with the best model you have, and then the validation is to see if what your model is actually learning is valid. You can say, let's say for example, you use the training. I mean, for the second split, you use the training data to train the model and the validation data to assess how good the model is learning from the training data. So in a sense, the validation data also becomes part of your training, because that's the data you use to test the model every time you change or you tune one of the parameters in the model. Does that
I think
answer?
it's sort of like if you're trying to really publish paper results and stuff, you need to save your test set until the very end, because if you're testing on your test set each time, you end up like making changes to your model just to like adjust it to whatever quirks are in the test set. Like maybe the test set got randomly split to be more heavily weighted towards one kind of, you know, example in your data set or something like that. And so the idea is that like last week we were testing on our test set each time to see if our model improved. And that's kind of a faux pas. That's not really what you're supposed to do. You're supposed to only test on the test set once at the very end. And so to see if your model's actually improving or not, we use this validation set. And it's okay to be testing on the validation set as we're going. And then we save the test set for the very end. Yeah, exactly. Validation is a reasonable test set. That's a perfect way to think about it.
Yeah. So Tyron said is if for honest validation on data you didn't see it. Yeah. Yeah. We got it. So I guess we can continue on this part on the bringing the feature to the same scale. So this is the thing here. Like when we look at the features, let's say for example, like sulfur dioxide, the maximum value is 54, or this one here, which is 289. When you compare these values, let's say to 1.58, 1.58, the difference is huge. So one technique, they are basically there's another technique which is called normalization, where you basically take the maximum and divide by the maximum of each column. But what we're going to do here is called standardization. Some people might change the names between the two. And what standardization is that you take the mean of one column. Let's say I take the mean of this column here, and then I take the difference of each value. I mean, I take to the mean. So basically, is every single value in this column minus the mean of the fit acidity, and then I divide everything by the standard deviation of each feature. So Sklearn has one tool for this and it's called standard scaler, and that's what standard scaler does. So basically, what you do, you basically just fit the data. So the way we can fit the data is so let me try this one. I have some weird names. This is the training. So we can do the fit, only fit, but you can also do transform. And what it's going to do is going to return the transform data, this data that you have here already standardized. So we do this for both. So here, I want you to be careful. Basically, you only do the fit in the training data. You do fit and transform the training data, and then do the transform on the validation data only. So are we missing? Am I missing anything here? Also, I have to transform the test data as well. So I guess everyone is up to here. So guys, I'm gonna have to ask for. I'm gonna have to excuse myself for using this weird names for variables. I know, I know. So this is the training. The one that has the TR. The testing has the TS. The one that has the V at the end. Oh no, this is okay. I hope everyone is up to here now. Is anyone getting behind? Oh, I didn't define this.
We could do this standard scaling before splitting if that's a little easier. Might be easier to just keep going this way for now, though.
Yeah, I guess so. I mean, okay. So can continue this part. Okay. So I guess we can just to see how it changes and how affects the model. And we can create a data frame. The way you can see the actual change. Oh man, where is it? That's it now. Okay. So we don't have quality is going and alcohol is going. Yes, you can see now the 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 values of each feature totally change. It goes from, let's see how drastic the change was. Basically, the minimum value is this one, negative 0.2. There's like 3.78 here. It's the minimum value. So all the features are in the same scale. And even when you do, so what I did, I got the columns from the original data set and basically copy and paste and erase these two columns. As a matter of fact, you can also do this. Create pause, first. I suggest doing this. You can create a list of the actual names of the columns. Good? So yeah, like all the features are in the same scale now. And when you check, oh, okay. This is another power plot. So something that I'm not going to do here because Seaborn takes too much time. And is that if you create another heat map, you're gonna see how the correlation changes. It actually increases the correlation. Yeah, it gives you a more visual understanding of. So why do we want to change the why do we want to bring all the features to the same scale? Is everyone up to here? If you're not, please let me know now. Okay, so this is the idea. So Like first, we can start by having a linear regression, a simple model, linear regression, and I have before I continue, I have to define the R square here. So this is another matrix we use for to determine how good the model is, and what the R square measures is basically what is the mean square error. Remember that it was defined at the top, divided by the variance of the actual output. So yeah, can continue here. We can fit the model, XTR, RDB, and YTR, RDB. So if you want to know, let me have it this way, so that way you can see it better. So these are the coefficients. Oh, yeah, I changed this. Never mind. Actually, let me do something real quick. So I take the inverse. What the inverse does is that it returns what the actual value is. Hmm. Right? No, it's not. So, uh, okay, yeah. So I made a mistake here because I wasn't supposed to standardize this yet. But the point is that when you standardize the data, you get basically the coefficients. They have a similar value. Like you can't even tell which coefficient has more importance than one another. Like you see the pizza acidity is more important than volatile acidity, and even the citric acid. So basically, this one here might cause some noise in the actual model, and the same as this one here, the chlorides. And you see, free sulfur dioxide. Remember that I told you that basically you have three columns with similar names, which is sulfur, and like basically these two here, these two columns, they don't actually they can uh, give some noise to the model and affect the actual learning of the model. And so for this part, what I'm going to do, I'm going to send you another notebook with the actual code. But yeah, so let's jump to this part here. Yeah, this is the part when the data was standardized. And you can see here it has the basically similar coefficients to the ones that I have here. Like even the error, like you can check what is the how you call this, the bias. So you can check the intercept extent. You can be working with this. So let's see how the model does. We can do widespread. Let me make sure. Let me. Oh, you have to standardize this. Check the mean square error. And this one here. Similarly, we can check the R score. Same thing for the test set. Y, right? Yes. Okay. Oh, there's something. This isn't right. Just to make sure that it's transformed properly. I have to check on that. Okay. So we are up to here. You guys want to take a break or Steve?
Yeah, let's take a break. Let's do a 10-minute break or just under 10-minute break and come back at 7:50. Yeah, we'll come back at 7:50. We'll talk about the projects a little bit. We'll make sure we understand where we're at with regression models, and then we'll talk a little bit more about how to tune regression models and how to do cross validation. So see you guys in 10 minutes. Alrighty, come on back. We're going to get started here in a minute. Carlos, can you turn off your screen share when you have a second?
Sure.
All right, come on back, everyone. I'm trying to decide if we should continue with linear regression and then talk about projects at the end, or if we should take a little break from linear regression to talk projects and then come back to it to finish up. Does anybody have a preference? I think let's talk projects. I want to make sure we got enough time to talk projects, and then we'll keep going with linear regression. So in the Kahoot, a lot of people said that they had done some exploratory data analysis on their data set. And so I'm wondering if anyone, I know I'm putting you on the spot, but is anyone willing to talk just for a second about what they did, what they were able to see about their data set, anything they struggled with, or anything that was successful? Were people pretty successful with their exploratory data analysis, or did you guys run into problems?
My guys.
Still struggling deciding on what we want to do. And you guys can come off mute for this sort of thing too to make it easier than typing a bunch of stuff in the chat. Sard, did you decide on a data set and you're trying to decide what to do with the data set? I can't remember what you were working on. Can you? Okay, so still looking for a data set. That's cool. Who was able to actually take a look at it? Maybe no one. So I'm asking because we're trying to plan out, we're halfway through our classes. We've got 4 more classes after this, and we want the rest of the classes to include some element of, like Carlos and I looking at y'all's code and helping you figure out any problems you're facing, or brainstorming ideas what to do and things like that. So we're trying to feel out the best way to make that happen. And so it could be that y'all bring, you put it on GitHub, and then you bring it to class, and then we can have 2 different meetups happening, one with me and one with Carlos, where we each have, like 2 or 3 groups of students, or I guess 3 or 4 groups of students. And then, we'll be able to work with you in small teams like that. It's a little bit harder virtually, so that's why we're trying to do some groundwork now to figure it out. So yeah, if you're just honest about whatever problems you were facing and things like that, just makes it easier for us to help you guys. And if the answer is that you had a bunch of midterms this week and didn't have time to do anything on your project, then that's totally chill. But yeah, what were some of the barriers? Like, Sar, is the problem just kind of not really understanding what's possible with this sort of project, and so having a hard time deciding what to do? Is that kind of the issue you're running up against?
I have a question. I noticed that some people said they have a repo for the project already. Are you guys willing to share the link with us so we can help you out? Or... Come on, guys.
Wait, are you asking if we're willing to share the GitHub
Yeah,
link? Absolutely, yeah. All the help we can get, that's fine.
yeah. So we can,
So I have an idea. Maybe this weekend I'll record a video where and okay, let me see this real quick. Um, so Julio used Excel to clean it up. Nothing wrong with that. Sometimes, especially if people don't put it in the right format, then it's hard to, yeah, sometimes Excel's the easiest way to clean that sort of thing up. So nothing wrong with that. And deciding on a specific data set is hard. Yeah, I feel your pain because it's hard to know what to do without kind of having the experience. But I think if you just have a data set that looks like it's coming from a quality source, um, and is in something you're interested in, then I think you'll be able to do something interesting with it. So that's why we were trying to encourage you guys to just pick a data set at the beginning. Okay, cool. So working on some data cleaning, doing some research on TensorFlow. This is great. This is perfect. I think what I was about to say is I had an idea, and let me know if you guys think this would be helpful. But I could record a video of like loading a data set that I haven't worked in before, and just kind of exploring it and seeing what's in there and training a simple kind of base model to get me started, just so you guys can kind of see the thought process that goes into starting with the data set from scratch and exploring it and things like that. Okay, cool. So we'll get that to you guys. And then you'll be able to kind of see what we do there as a base to guide your own exploration and things like that. So let's say we have spring break next week and we don't have class. And then I think I'll actually check with Edgardo about this. It seemed like he had asked before we started teaching if students wanted to come on the 16th. And it sounded like we were going to have class on the 16th, but I'll verify that. And if you can't make it to class on the 16th, that's all right. But I'm talking about our class schedule because I'm trying to come up with, some guideposts for where the project should be. And I would say by next class, we definitely want to have like a data set picked and a clear idea of what we're trying to accomplish with the data set. So if we're trying to do some machine learning, we need to decide what feature or, what the label is, what we're trying to predict, and kind of have like a base model up and running. And if we're trying to do a visualization, we want to have a idea of we can, yeah, I don't think we have class next week, but I'll still be on Slack. I don't know what Carlos's plans are, but if you have a question while you're working on something, I would still be happy to answer it. But we will not have class during our regular time next week. That's right. Cool. Does anybody have anything that they're excited to share that they did on their project before we move on? Don't be shy. You could inspire, you could be a hero and inspire the rest of the class. Anyone have a data set? And that's a good question, Carol. The answer is I don't know. We can talk about that after spring break. Yeah, so it'll be virtual almost assuredly. And yeah, we need to think through that with the rest of the CTP team. And yeah, so we'll have a plan for it to give you guys plenty of advance notice, but don't have a plan yet. We'll figure it out. Gurjeet loaded the data set. It was exciting. Gurjeet, what's the data set that you're using? Was it the property value one that we had been working on?
Yep, it was that one.
Sweet. Were you able to, how did you download all of the separate links from that website, or did you end up just picking one of them?
So I did like a test one, and it wasn't a very a large data set. It was just small, and I wanted to make sure I can manipulate it before I get on to, you know, having a lot of data to work with. Um, I had a little bit of an issue where, okay, I don't know if you can put PDFs on here, so I converted it into a what is it, CSV file, and that sort of corrupted it a little bit because when I opened it up, it got a little messed up, and there were some extra columns in there that weren't there before, so I had to go into Excel and fix it. Yeah.
That's interesting. I remember there was a CSV option to download. I think maybe it depends on which exact page on the website you're on. But I didn't even, so you converted from a PDF to a CSV. I didn't even know that was possible.
Yeah, I did.
That's funny. Cool, 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 cool. Any other, Julio made a pie chart. That's what EDA is all about. That's what we're here for. Julio's got it figured out.
What are you working on, Julio?
Sorry, what?
What's your data?
What's your project?
I did a pie chart on New York City's demographics, like different races, ethnicities.
Okay.
Yeah, but that's about it. I think we're going to use more data, but
Uh-huh.
I guess it's a start.
Where are you getting the data from?
New York City Open Data.
Okay. Oh, good.
It's kind of old, from 2016, I think.
Uh-huh.
I couldn't find anything more recent.
Okay.
Sweet. Sarah, are you trying to share your screen? I see, or is that just like an artifact of my? Your video looks like it has a notebook in it, but I think that's just an artifact. I think Meetup's just confused from when Carlos was presenting. Cool. Thanks for sharing your update on your project with us. So yeah, like I said, we want to be more involved with the projects, helping you guys out. We're gonna set aside some time next class to kind of split up and be able to give some more one-on-one help and things like that. So we'll come up with some specific instructions for what to have ready by next class, but should definitely have data set picked out, have an idea of what it is you're trying to accomplish with the data set, and then have loaded the data set into Pandas, done some exploratory data analysis, and hopefully created a base model with a reasonable level of accuracy. So we'll, like I said, put a sort of tutorial up for how to do that on a data set that's new to us, so you can see how we think through it and things like that. And then we'll go from there. So let's go back to regression. And I think we might end up ending a little bit early tonight. I don't know if I'll end up presenting for a whole hour here, but we'll see how it goes. So first off, any questions from the first half of class? So to recap what we just talked about, maybe I'll even just have you guys explain some things back to me to make sure we're all on the same page. So to start with, who can explain, and feel free to come off mute if that's easier, but who can explain why we split the data into a training set, a testing set, and a validation set? I will volunteer somebody if I have to. Oh, go ahead. Thank you.
I'll go. I think so. It's like you don't have cross-contamination. So like if you train your model using, you know, all of your data, then how are you going to test that? If you test it on that data, then you're just going to get, you know, not a super accurate response. So you would want to split them up. That way it's all new to the data that you're making.
Perfect. That's good. And then why do we do the valid? So that's why we split into train and test. And then can you say why we added the validation in on that kind of framework?
Stumped me there. Stumped me there.
You can help Meldon out. Meldon was brave. and volunteered. Why do we have a validation set in addition to our train and our test set?
So we don't overfit or underfit.
So it is related to overfitting and underfitting. Yeah, so that was a good example in the video. So Nissan mentioned, so it's not like using the exact homework questions on a test. And so that's good. That's why we split into a test, because it's hard if you just look at your accuracy on the training set. So we could take our regression, we can actually measure our R squared on the training set, or if we're doing a classifier, we can measure our accuracy on the training set, and it's not going to be perfect, right? Because the real world, there's variance in everything. You could have two examples that were exactly the same on all their attributes, and then the label was different. So no matter what, you're going to have an error on the training set. But if you're just looking at the error on the training set, it's like testing a student on questions they've already seen before. The model can just memorize the questions it's seen, and you don't have any sense of if it generalizes to new data. So that's why we do the test set. The validation set is so that we're not continually testing on the test set. Like, I can't remember who said it earlier, but it's like a reusable test set that keeps us from being too focused on increasing accuracy on the test set. We really want the test set to be removed until the very end to like serve its best purpose of helping us understand how our model's generalizing. And so that's why we have the validation set. What else did we just talk about? So why do we standardize? What does it mean to standardize our data? First of all, I guess, what does it mean to standardize the data? What were we doing there? What does it mean to standardize? Going once, going twice. Someone take a guess. Give us a starting point. Good. So it's rescaling. And does anybody remember how we rescale it? Yeah, you can always Google the question if you don't know. So the idea is that with regression, if you have a feature that's a lot bigger than the other features, it can skew your model simply because you're adding and multiplying things together. So if you're taking something that's in the millions and adding it to something that's in the single digits, the single digit gets totally washed away, right? And so a regular regression, like if you don't scale, the regression kind of works itself out because it ends up multiplying that number in the millions by by 1 over a million to get it down anyways. But that's just kind of a messy solution. So the much cleaner solution is to scale things ahead of time before feeding it into the model. So that's what we were doing with the standard scaling. And the way it works is it makes it a normal distribution. So you've probably heard of a normal distribution before. That's the bell curve from statistics. But the exact definition of a normal distribution is that it has a mean of 0 and a standard deviation of 1. So what we do is we take our data, we subtract the mean from every value. So I want you to think about that for a second. If I've got a series of numbers, let's say it's like 1, 1, 2, 2, 3, 3. The mean is 2, right? I think so. So I subtract 2 from everything, and I get -1, -1, 0, 0, 1, 1. And so now my mean is 0, and my numbers are centered around 0. So it's not that every number is 0, but every number is, the mean is 0, and every number is centered around 0. And then to get the standard deviation to 1, I divide everything, you divide everything by the standard deviation. And so that gives you a standard deviation of 1 as well. So that's what the standard scaling was all about. And it's a way to make our regression models a little bit better. And so it's an important step there. Okay, good. Those were the two main concepts. Any other questions from the beginning of the lecture. Let me share my screen. Great. So you guys can see my screen. Someone drop me a quick yes in the chat. Sweet. Thank you, Gajit. All right. So what we're going to talk about now is a slightly different kind of linear regression. It's called lasso regression. And it has a close cousin called ridge regression that's very similar. And what they're both trying to do, lasso and ridge regression, is to introduce regularization into the process. So this is the key word here, regularization. And when we're talking about regularization in machine learning, usually what's happening is we're adding something onto our cost function to like get the model to behave how we want it to behave. And so that's kind of a hand-wavy explanation. But what's happening here is let's look at this equation here. And this is a cost function. Does anybody who can tell me what a cost function is? We went through that kind of fast at the beginning. So let's see if anybody caught that. Otherwise, we can talk about it again real quick.
Kind of like the penalties of the prediction.
Perfect. Yeah, that's exactly right. So the cost function is what our algorithm uses to learn. And it's you're right. It's a penalty is a good way to think about it. It penalizes bigger mistakes more. And so what we're actually maximizing, if you like look at the math of the algorithm, is we're trying to get our cost function as close to 0 as possible. So the algorithms are all designed to make predictions, measure the cost function, and then make changes to get that cost function closer to 0. And so the first part of this cost function, this part that I'm highlighting here, that's the regular linear regression cost function that we were using before. So it takes your yi as your y hat is your prediction, your yi is your actual value. So it subtracts them and then squares it. It squares it. Does anybody have an intuition for why it squares it? I'll give you a hint. If you wanted to, you could take the absolute value instead of squaring it. Good. So Nissan says to get rid of negatives. If we had negatives in here, we're adding them all together, and those negatives will cancel out the positives, which is not what we want. We want the total error. We don't want some of our errors to cancel each other. So we square it, we add it up together. And so our cost function is really simple. It's just the squared error of our predictions. But now we're adding this extra piece here. And so what's happening is we're taking the weights. This W is the weights of our model. We're taking the absolute value here again so that we don't have negatives and positives canceling each other out. And we're summing up all of our weights. And so why would we want to sum up our weights like this? And it's actually kind of related to what we were talking about when we were talking about standard scaling, is that anytime you have large numbers in the middle of these models, they kind of have, they just, they're throwing their weight around, they got a lot of clout, and they just kind of skew everything in a way that we don't want. So what we're doing by summing the weights here is part of our cost function. What we're doing is we're penalizing large weights in our model. So I want to let that sink in and make sure we understand how this equation is penalizing large weights in our model. So if we have large weights, this W is our weight. So if we've got, some weights are hanging out around 0, we've got some ones, we've got a couple numbers below 0, but then we've got a weight of like a couple of thousand in there. That couple of thousand is going to get summed up. This sum is going to be large, and that's going to make our whole cost function larger by having that large weight in there. So by introducing this term at the end of our cost function, we're telling our model to prioritize smaller weights. And again, there's nothing like, this is just kind of something that's like a conventional wisdom, is that we want to have all of our values close to zero. We want to have all of our weights close to zero. It just makes it easier to deal with. It makes it easier to interpret the coefficients when we're looking at them ourselves. And then the last thing here is this alpha value in front. And so that alpha value is a parameter that we choose, and it determines how important this weight part is to the rest of the model. So if this alpha value is like a number like 1 or greater than 1, then we're putting a lot of importance in this term. If it's a number less than 1, like 0.1 or even 0.01, then we're putting less importance on this. We're putting more importance on the actual predictions, less important on this weight term. So yeah, that's how lasso regression works. Where main idea is that we're getting our model to prioritize having smaller weights, which is a characteristic we want of our model. Next topic is cross-validation, an important topic in machine learning. What it does is it's kind of a new way to do the validation. And so what we do is we split 10 is a common number. So in this example, we've split our training set into 10 different splits. And we're going to train on 9 of those splits and test on the 10th one here. But then whichever of those 10 that we're testing on is going to change, and we're going to end up testing on all of them. So we're going to split it into 10 different groups. The first time through the data set, we're going to train on the first 9 groups and test on the last group. But then the second time through that testing, whichever 10th of it we're testing on is going to change, so that by the end, we've tested on all of it. And so it does a couple of things for us. It lets us use the whole data set for validation, which can be nice. So sometimes you can just randomly end up with a validation set that's not really representative of the whole data set. We use the stratify parameter in the train test split to kind of avoid that, but it can still happen sometimes. So by doing this cross-validation, we're making sure that we're validating on actually the whole data set, which can give us a better idea. And it's like, we saw this last week, where sometimes you just kind of get a model that performed better or worse than average, just because it's a random process. And so by doing it 10 times, you just kind of get a better sense of what to actually expect out of your model. So we're going to do cross-validation here too. So follow along with me as I go through this. If I switch, let me try this. If I switch my window, do you guys see Slack, or do you guys still see the, you still see the notebook, right? Okay, perfect. So follow along with us here. Oh, now I got to get my alt tab sorted. There we go. So we're going to make a new lasso, and the command is just lasso. So that's the command we imported at the top. That's what this will do, a new model for us with this cost function instead of the regular linear regression one. And we've got a couple parameters here. We're going to set our random state so that we're all getting the same results. And we're going to set, I actually don't even know what this does. Do you know what this does, Carlos? Selection? It's all right.
I forgot, man. I forgot.
Yeah, it's all good. And then what we're going to do is we're going to use this grid search CV. So grid search CV. And let's go ahead and look at the documentation for this guy. So this is what's going to do. This is what's going to do our cross-validation, but it's also, so CV here is for cross-validation. But this grid search here is a technique for finding the best value for whatever parameters you're putting into our model. So if we go back here, the parameter that we're going to be grid searching for is this alpha. Remember when I was talking about this alpha is just a value we pick. It could be a 1, it could be a 10, it could be a 0.1, it could be, like you could set it to pi or something if you wanted to. But we don't know what the best value for this alpha is. And there's some like guesses you can make. But the best way to do it is to just test with a bunch of different alphas and see which one works the best. So that's exactly the idea behind this grid search, is we're going to give it some different values for alpha. It's going to train the model for each of them, and then it's going to report back to us which one was the best one. Does that kind of make sense, the idea of what this grid search is doing? Let me know in the chat if you followed that explanation, or if you want me to spend some more time talking about what we're actually trying to do with this grid search here. So to reiterate, we're going to do this grid search and we're going to do cross-validation. And it's going to go through this validation. It's going to change this alpha value, and it's going to report back to us at the end which alpha value had the highest accuracy on the validation set. So let's look at what we need here. So we need to feed it the model. We need to feed it the actual parameter we want to look at. I have too many windows open now. So this param grid can be a dictionary. That's what we'll do. The estimator is our model that we just initialized. And then this cross-validation, we're going to input as well. So we're going to say, sorry, I'm having a hard time navigating back and forth here. We're going to say lasso. We're going to say CV equals 10. And then we need our dictionary of alpha values. So parameter. And we tell it alpha because lasso here has a parameter called alpha. And we're just going to give it a couple magnitudes of 10. And then we want to feed that dictionary into here. And then we need to set this equal to something. Perfect. Let's see if this works. Great. Any questions about this step really quick? Any of the arguments that we have here, what exactly it is that we're trying to accomplish? Cool. So we're going to scale our data again. Let's make sure we understood what happened here. So we initialize our standard scalars. We fit transform on the training data, and we transform the test data. I think this, yeah, we'll see what happens. I think when I was working with this earlier, I might have had something other than this RD here, so we'll see what happens. And then same thing for our Y, we fit transform on the training Y, just transform the test Y. And then we have to actually fit our lasso. So we're going to do dot fit. We're going to give it our X train. And our Y train. Sweet, that was actually faster. So a lot of times when you do this CV here, this cross-validation, it takes longer. But it seemed like that was good. And then so to get the best parameter, I think it's best params underscore. Okay, so it looks like it was the same as before. So it tells us the best parameter for alpha, so the one that had the highest accuracy on the validation test set is this 0.01. Sorry, 0.001. So that just means right here we're going to have a 0.001 in this cost function, which is actually telling us that this regularization isn't doing too much for us, but that's okay. So let's look at our coefficients.
Steve, research doesn't give you the coefficients.
Yeah, that's right. Is there? Oh, this is just the one from above, isn't it?
Yeah.
Is this the coefficients we had before? That's
right. I guess you're gonna have to create the lasso straight without.
Yeah. Okay. We'll do that real quick. So we'll just set. Yeah. We'll just. Okay. We'll do it down here. So now we're just making our lasso model again. It was just lasso, right? Yeah. And then let's look up lasso, see what.
You got the alpha now.
Is it just alpha? That's what I was looking. Yeah, so it's just alpha. So to set the alpha, we do alpha equals 0.001, which is the value that it told us was the best. We're going to fit our lasso. Grab the same thing from up here. Our lasso is fit. All right, cool. And then we're going to plot our coefficients down here. So let's just take a look real quick. We can look at our coefficients before we plot them. So we can do lasso coefficients. So these are the coefficients of our model. I wish I hadn't run this block because it used to have our old coefficients up there. Give me just 1 second. Let me see if I can easily get the. I think it was LR. Let's try that. Hey. So these are our coefficients, just regular linear regression. These are our lasso coefficients. It's kind of hard to read that, so let's plot it. So what this is telling us is this is just telling us the magnitude of our coefficients here. And remember that we're regularizing so that our coefficients are closer to 0. I actually didn't mention this, but one of the ideas of getting our coefficients close to 0 using this lasso regression is that if the feature isn't adding much to the model, so like this feature here, this feature here, this feature looks like it's exactly 0. Is that right? No, just super close to 0. That's this one. And this one, if we're doing regular linear regression, we don't actually want to throw too many features in because it can confuse our model. The more features you put in, you can get your R² score to go up. When you add a feature to a linear regression model, the R² score never goes down. It can only go up. And so this is kind of a problem because it's important to know which of the features are actually contributing to the model and which are extra. One solution to this problem is to use this lasso model, which will take those features that aren't important and set their coefficients close to 0 anyways. So that's a good reason to be using this regularization too. So we can see the features that are important here are the acidity, the density, to a lesser extent, the pH and the residual sugar. Cool. Any questions about this so far? So what we're going to do is we're going to try just looking at some of these important ones. So we've got fixed acidity, citric acid, residual sugar. Notice we skipped volatile acidity. We're going to skip chlorides. We're going to skip free sulfur dioxide. We'll keep total sulfur dioxide. We'll keep density and pH, and we'll keep sulfates. So we ended up dropping volatile acidity, chlorides, and free sulfur dioxide from our model. Like I said, because we don't want to have any extraneous variables if we don't need them. Oops. Sorry, so some of my variables have been renamed here. So it worked here, but not here. Oh, it didn't work there. I didn't actually run that one. Shoot. So this is our standard deviation model, or our standard scalar model, standard X-train, RDV standard. So I think that's just this, right? Let me check the filled notebook real quick. Sorry, guys. We can just do it on, all right, we'll do it live. So what we're going to do now, we're going to rerun the same model with this new columns list here with 3 of those extraneous ones dropped, and we're going to see how we do. Let's actually get so let's run this one, make sure these worked. Okay, cool. Sorry for jumping around my notebook so much. There we go. So I can spell columns. All right, sorry guys. I got my variables mixed up somewhere back there. I won't make you watch me try to figure it out. But if we reduce our data frame to just these columns, the ones that had the most importance, we get our new data set just with these columns. We can train our lassos just on these new columns. And if we train our lasso regressor using the parameter from the alpha, we can look at our mean squared error on our training set, and it's going to be 0.31. We can look at our mean squared error on our test set, a little bit higher, but still good. R squared on the train is 0.7. R squared on the test is 0.6. Two reasonable two reasonable values for an R-squared. And then we get into plotting our residuals. So we'll talk about that in 1 second. Did any of you guys get your lasso regressions to work on your on the data set here where we drop the columns? Was anyone able to make that happen? Seems like a no. Going once, going twice. Yeah, I think we all had the same problem where we got our variable names mixed up. Let's just, you know what, this will be a good exercise to see if we can get it working again. So we're just going to start. So it was, I keep saying this as win equality, which is kind of funny. And don't forget the delimiter needs to be a semicolon.
Steve?
Uh-huh.
We were using the red wine data set.
We were using the red wine, that's right. There we go. All right, so then we want to, let's do our standard scaling first to save us. So let's do this. Let's do our features equals df with these values. Oh, you got to have two brackets when you're subsetting like this. Make sure that looks good. Sweet. And then what we're trying to predict is we can just call df.alcohol. So make our standard scalar. So this is a good look at our process from beginning to end too. So features equals fit transform. And if we look at our features again, we've got an array instead of a data frame. Notice that. And then our values have been changed to be mean of 0. So that's what we wanted. And now we can do our train test split. So train features, test features. Let's do the standard scalar on the what should I call? Coming up with names is sometimes the hardest part. They're not labels. Let's call it Y. I guess technically you're supposed to do it after the split to so that your transformer doesn't fit to the test values as well, but that's okay. Oh, come on. Can you not do a fit transform on just a single series? Do you know, Carlos?
No, man. I don't know why, but I have to shape it.
That's annoying.
So just do the reshape, and for the first value, have the number of rows. No. Have the. Okay, yeah, it
I
worked.
think that worked, yeah.
Yeah, that's good.
Cool. So we've got our features, we got our values. We're gonna do train features, test features, train y, test y, equals train test split. Um, and then we stratified on quality last time. Let's actually see what would happen. I don't know if this will work. Hey, did it work? That's cool. So even though we dropped this quality, it looks like it was still able to stratify on it. So that's cool. So let's make sure these look right. That looks good. That looks right. Sweet. And now we're going to do it again. So we'll have our train features, our validation features, our train Y, and our validation Y. And it's just another train test split. Oops, train split. Train test split. But now we're splitting, instead of features and Y, we're splitting only on our train features and our train Y. All right, so sorry this took a minute. We can't stratify it. That's okay. Sorry this took a minute, but hopefully that's a good, good little recap of how to do these things and why we're doing them and things like that. All right, so now our new lasso. I typed this up before, didn't I? Great, so we've got our alpha equals 0.001. We're gonna fit it. And we're gonna fit it to our train features and our train Y. Great. And now we're going to predict, let's see here. What did we do in the filled out one? So we'll do train predictions equals lasso.predict train features. Validation predictions equals lasso.predict validation features. Test predictions equals lasso.predict test features. And then we can do mean squared error. I think this is the right one. Let's start with train. Oh, you do? So remember, you always do the ground truth first. So we had a little bit higher error than we had when we ran it before, which could be random, could be because we did it slightly differently up here, where we didn't stratify on quality the second time, or on, quality the second time. There's probably a couple other differences you can find in here if you looked closely. So doing it this way, we had slightly higher error here, which is worth paying attention to. Let's look at the validation one. So this validation wasn't in our training set, so it should give us a sense of how we'll do on the test set. I think that was actually higher, wasn't it? Let's look at both of them. I mean lower. Cool. So maybe a sign that we're underfitting here. And then let's look at our test. And so our test is a little bit higher. And then we can do the same thing for R-squareds. The command's R2 score, I think. Let's just look at our train. Six, 5, not the best score, but also not bad. Our validation, our validation set's doing better than our train set. Cool. And our test set's just a little bit lower than our train set, which is exactly what we would want to look for. Great. So what we're doing now is we're plotting our errors. And so this is, let's see if we can easily, okay, so these are defined. And so let's see if we can do this with our new variables. So we do plot error, and then we're doing, let me actually make sure. So plot error prediction, and then we're doing our training, our Y train, and our, what is this? Okay, so our actual, yeah, so our actual Y, and then our predictions. Does that work? Ooh, okay. Great. And so what is this? So what this is doing is it's taking, and we can look at the function up here too. The important thing here is that it's taking for each pair of predicted and actual values, it's just subtracting them to get the error. And then it's plotting each of those errors as a function of the Y hat, which is the prediction. And so the reason we do this is because you're looking for patterns in this graph here. If it's the case that, especially a parabola is the best example. So ours is pretty randomly distributed here, which is exactly what we want. I don't really see any patterns. You guys let me know if you see patterns, but to me it just kind of looks like a point cloud here. And so that's a good sign. What you want is for it to look like a point cloud. There's a couple of things. Let's just find some examples real quick. So these are called residual plots. I've been to this website before. Okay, good. So here's a good one. So here's one where you can see a pattern, and this is the classic funnel pattern. And what's happening is that your predictions are really close to the actual value on this part of the graph. So remember that it's the residual, it's the error. So it's your prediction minus the actual, or reverse, it doesn't matter. But it's close to 0, which means your prediction was accurate. But as you get up to this second half of the graph, they start to become a lot less accurate, and you get a shape that looks like a funnel here. And so that's related to something called heteroscedasticity, which is a fun word to say. And it just means that your predictions, your residuals are getting larger as the predicted value gets larger. And so it means that so this is the actual thing you're trying to predict. It means that your values are more variant over here. And so this is one that's less of a problem and more of a thing to kind of be aware of. Yeah, I don't even know what you do. Do you know, Carl, is there a easy fix for heteroscedasticity? What I really want to talk about is this nonlinear one.
Oh, I don't know, but it's more like a trial and error thing. So,
yeah. But the real reason we do this is to look for these sorts of patterns here. So if you see a pattern like this, what it means is that you have some nonlinearity in your data. So all of these models are linear models. If our residuals are looking like this, we need a not linear model. So we could just switch to a different model that's able to capture these nonlinearities. Or what we could do is we could figure out where the nonlinearity is coming from and just square the value before feeding it into our regression. But this is the real thing to look out for on a residual plot. You can also have some situations. Let's see if they have it. Yeah, so this is another good one, is if they're all clumped together and you've got one or two off in the distance, you've got some outliers, you could just drop them from your data set or find another way to deal with them. But yeah, our residual plot looks great. Here it is versus the Y. This one actually looks like it's got a little bit of movement to it. It looks like we're, for the higher alcohol contents, it looks like we are under predicting. So I don't know how we could address that in our model, but that's something that's kind of interesting to look up. Do you guys see what I mean here in this residual plot? How up here we had a nice point cloud. Down here, like this half is mostly below the line and this half is mostly above the line.
Steph, you need to run this graph first. This is what
okay, yeah. Well, it's still interesting that that's what you got before, right?
I mean,
so what is this?
It was a good example.
So Y train, is this on the test set?
Yeah.
Or is this okay?
No, that's the chain set. Yeah.
A little bit less pronounced, but still the same. Yeah, exactly the same. Do you have any ideas about why it looks like that, Carlos?
Not really. I guess the strategy here will be to start taking columns out and see how it changes.
That's
so
good.
Maybe there is a high correlation between some of the columns remaining.
Okay, yeah, that's good. Sometimes when you have a correlation between your columns, that also influences your regression model. And when we talk about unsupervised methods, we'll talk about, so we scaled the inputs to our model to have a normal distribution, a mean of 0, and a standard deviation of 1. Principal component analysis is the technique you would use to reduce correlation between your inputs. And that's something that we'll be covering in the future. So let's stop here. We've got some more residual plots. You can use the same technique we used above with the grid search on other models besides regression. So it's not something that's specific to regression. It's the idea of finding the best parameter by testing a bunch of values. You can apply to any sort of model, including SVM and things like that. So that's what's happening at the end of the notebook there, if you want to check that out. But let's stop there and see if anybody has any questions about the material that we covered today, or about next steps for the project or things like that.
Any questions, guys? So remember, next week we have the office hours. Please, I don't want to say stop by, but show up if you have any questions about the project or anything. So we have Mike. Anything else besides picking a data set for next week? Anything else?
So for 2 weeks from now, I would say pick a data set, load it into pandas, and do some exploratory data analysis, and have a clear picture of what you want to accomplish. So I just mean, if you're going to predict something, what exactly it is that you're trying to predict, or if you're going to visualize something, exactly what you're trying to visualize. If you're trying to predict something, it would be awesome to just make a really, you to make a really simple model, you can just come in and copy some of our code where you do the train test split. You can just do a regression or a decision tree and fit it to your data. And then you can see what kind of results you get on the test set. But just sort of a base for which to make some more improvements. They're saying if you're doing a visualization, it would be cool to make a really simple version of the visualization just to have something to work off of. And that'll be over the next 2 weeks. So I think you guys will be able to accomplish that over the next 2 weeks. Like we said, we'll make a video and put it out soon, kind of walking through all those things I just mentioned on a data set. And yeah. Other questions?
All right, guys. Any questions?
Can you guys hear me? I just crashed.
Yeah.
Cool. Well, were there any other questions while I was gone? I assume not.
No. No.
Cool. Well, thanks for stopping in, guys. Good to see you. Next week, be ready with your projects, and we'll spend about at least half the class helping you guys on your projects. Stopping on our office hours to work on your projects as well. And yeah, be safe out there. Have a good. Sorry, did I? If I said next week, I misspoke. 2 weeks from now, no class next week because of spring break. And yeah, stay safe. See you guys soon.
So just to get everyone know, I just committed the field notebook to GitHub. If you guys have any questions and yeah, stay safe. All right. All right, guys. Enjoy the weekend.